What's up, everybody? I hope you're having a good day. Today we're looking again at the Arlo Q security camera by Netgear, and we are going to be reverse engineering some firmware. If you've watched our last video, you saw that we pulled the flash chip off of the device, we read it with our firmware reader, we put it back on the device and got it operational again, and now we're going to be unpacking that firmware, taking a look at it, and trying to understand how the bootloader security mechanism is implemented and how we might be able to bypass that. So let's jump into that and share my screen here. So as we saw before, this is the prompt that we are getting when we interrupt the bootloader's normal flow and we try to enter into the bootloader menu. And it's presenting us with a prompt to enter in a bootloader password, and then as we noted before, there's this not so good thing happening that it's echoing out the SHA-256 sum of whatever I type into this prompt, clearly demonstrating that the password is probably stored as a SHA-256 hash. These were my hypotheses, and I kind of alluded in the last video that I've confirmed a lot of these hypotheses, and so we're going to take a look at that in the firmware. So what we're going to do is we're going to go over to my other terminal. So I have the firmware file here, and so let's go back and just show you that I've got a whole 256 megabytes of a firmware file. And so at first when I was looking at this file, I was thinking, oh man, to figure out what the password hash for this bootloader password is, I'm probably going to have to load this firmware, the bootloader, into Ghidra, which is going to be nasty because I don't know what the start address is supposed to be. It's going to be a big static binary with no references at all, and so it's just going to be a pain to reverse engineer. But this is something that I want to stress to everyone out there who's trying to get into hardware pen testing. Don't just go with the tool that the one path you think you're going to have to take. Always take a step back and ask yourself, is there an easier way? Have I looked at the easy methods that I might be able to get access to the thing that I'm after first before I go down some harder, long rabbit trail to get something I want? So what's the first thing I do sometimes when I'm looking at a big firmware program? You know, you might run strings on it, right? It's kind of like the classic example that you might do in a CTF, and you're like, yeah. Only in a CTF would like strings ever get you anything, like, and that's probably in the easy challenges, right? But in real life, it helps us sometimes as well. So using our extremely sophisticated method of reverse engineering this firmware today, strings on this massive firmware file. Now, this is a massive firmware file, so I'm going to pipe that into less, and then less has a cool thing where I can kind of use the Vim syntax to search. And so I'm going to pop back over here, and what I'm going to do is I'm just going to do a search for this prompt that I'm getting, because I'm assuming that all of the string constants in the binary of the bootloader that are related to this password are going to be adjacent to each other, right? So this is just a really quick and dirty, simple way to find really interesting strings is to see what are adjacent strings to something that you're interested in. So let's search for this string, and right next to that string we see, very curiously, what looks like a SHA-256 hash. And then we see all other sorts of strings that really give us a strong indicator that we have found the SHA-256 password hash that is hard-coded into the Arlo Q bootloader. So you can see here, it's even got the text of the prompt that we're seeing over here in our UART console. And we see various, dialog prompts, right? So right after this hash is the string password OK. Well, that makes sense, right? Because whoever's writing this program, the code to this bootloader problem probably goes something like, if the hash of the password that the user gave us equals this statically stored hash in the binary, then we're going to print out to the screen password OK, and then we're going to, allow them into the menu, right? So this is all making sense. We've totally found our password hash. And so later in a future video, what we're going to do is we're actually going to try to modify this firmware. Today we're going to show, talk about one potential method for attacking this, which is cracking this password. I've tried to crack this unsalted SHA-256 hash. I've thrown a lot of passwords at it, and I haven't gotten any luck with that yet. So the next option is going to be to do firmware modification, where I pull the chip back off again, and I write a new firmware with a known password hash that I know. So, but let's do some more reverse engineering, because to prepare for that firmware modification, I want to understand a little bit more about this system, the underlying Linux root file system, and especially the boot up process of this device. So what I'm going to do is I'm going to go over here. Let's just clear this out. So this is the results of what binwalk has given us. So when you run, binwalk-e, whatever the name of the firmware file is, it dumps you a folder that looks something like this. You'll see a lot of raw chunks of the binary. That's what all these things are. It's labeling it with the hex address of where it found, where it carved off a specific file, and then it attempts to unpack things like file systems and compressed files that it finds inside of a firmware blob, a firmware image. So the two important things we see here are these two squashfs root file systems. And so exploring these, we see that these are really similar file systems. So just really at a high level, you can see that that clearly looks like a Linux root file system with everything you need. And then we see a almost identical second file system there that are in our system. Let me get that up above my video feed. We can see that they're just kind of labeled. Those are just two different file systems. Again, here you can see the raw file that was carved off here, that there's these two different addresses where those squashfs file systems started. So this is one address, and this is another address to where those squashfs file systems begin in the firmware image. So why are there two of these? Well, on embedded systems, oftentimes what you'll see is that there is a primary and a secondary, an active partition and a backup partition. And these are often used when a firmware update is applied, right? So on an embedded device, if your firmware update causes some problem that causes the device to be bricked, that's not good, right? So typically what you'll have is an update mechanism that will have an active, the active running, like working Linux system in one partition, and then it will apply an update to that backup partition, and then it will tell the bootloader to say, hey, flip the switch and change the active partition to use in your normal boot up process to that other one. But it involves some mechanism that can detect if it's boot looping, or if it just crashes. If there's some kind of crash in that other firmware, there's some kind of recovery mechanism that allows it to switch back to that other partition in the case of an error. This is really common on these devices. And so what I find really helpful when I'm trying to figure out what does that boot up process look like, I want to let the device boot up. So we're going to go back over to the UART console. And so scrolling up here, I have a snippet of a typical boot, no button pressing, no trying to interrupt the bootloader. And there's some really interesting things that we can see here. So the one key thing I always want to look at is the kernel command line. So here is the kernel command line in the Linux boot up process. This is going to be fairly early in the boot process because these are basically passing arguments to the kernel, to the Linux kernel as it's starting. And so these are passed to it by the bootloader. So the bootloader passes it a set of arguments, and then the Linux kernel takes those arguments and starts up the Linux system. So one really interesting thing that I'm seeing here is that it's saying that the root file system it's set to use when it boots is 31:08. So that 08 part is really interesting to me because when I go down here, if I scroll down a little bit, it actually really nicely shows me a breakdown of the different partitions on the NAND flash. So it's just printing this out over the serial UART console. And if I just kind of do a simple count of these, starting with 0, because we know computer scientists, we always start counting with the number 0, not the number 1, right? So we count 0, 1, 2, 3, 4, 5, 6, 7, 8. And so keep in mind that 31:08, that is referring to a partition, the 8th partition or the 9th partition, right? So partition number 8 here is the one that it has selected, and then we kind of see that validated by these lines down here. It says partition LNX, you can read that as Linux, the Linux partition, right? Set to be root file system, right? And then we also see a validation of the unpacking of the firmware that we did. So back here, let's go back over here. We see these addresses that Binwalk named these two squashfs file systems as, 21, 20, 000, and then we got, 762. Nice. So we have those hex values. We see the same exact ones over here for this back partition and the Linux partition, right? So again, this is starting to make sense with that paradigm of you have an active and a backup partition for performing updates. And then this is going to make sense of another thing that I found in the firmware image. So when looking at those two squashfs root file systems, I wanted to figure out, okay, what are some of the big differences between these two systems? Now there's a lot. You can run a recursive diff, but I wanted to kind of focus in on a couple services that are really important on this system. And so one of them that I found was in a file. So let's actually run the diff command here. So we'll run it on squashfs root etc initd. So initd is a folder that stores services that can run on boot, that can run when the system has started up. And so there's a number of them here, but we can see that there is a Arlo service. And so I want to run a diff. I want to see what the differences are between that version and the other partition. And so what we're going to find are some very interesting differences here. There's actually quite a few differences, But there's a very important difference right here at the end of the file. So here we can see that one of these partitions has commented out this GPIO read command, and then it's changed up a piece of logic that uses, or doesn't use if it's commented out, a GPIO read. So what does GPIO read do? So in a hardware device, GPIO is a mechanism so that in software we can detect if a hardware button has been pressed or interacted with in some way, right? And so we can see that one version of the firmware is commenting that out. And if you haven't watched our first video on hacking the Arlo camera, we discussed previous research by the Flashback team, where they talked about a kind of backdoor in this camera, where if you hold in the sync button while the device is booting up, you can get it to have a live shell prompt over the serial console. Whereas if you don't do that, you can read, you can see the output of that console, but you can't actually send anything to it. It doesn't actually give you a shell or anything like that, right? And there was a number of other debug utilities that also were activated by the holding of that button. So let's go look at the version of this file that has has commented out and modified this logic here. So we can see here, this comment is left over from the old version of it, and we can see here, right there in the comment, it says allow serial shell if production test flag is 0. So if it's not a production device, if it's a testing or staging device, then you can have that serial console on. Okay, cool. We have a production device, so that doesn't really affect us. Or it says, or if the WPS pin is pressed. In the firmware, it refers to it as the WPS pin. In here, on the actual camera, it refers to it as the sync button, but that is effectively the WPS button on the camera, and that's the exploit that the Flashback team discovered in this device. So clearly it's been patched, and the active firmware on the device is the patched version of this firmware. But if we could get into that bootloader, we could update those kernel command line arguments that are passed right here. We could update this if we can get into the bootloader, but the bootloader password is in the way, right? So we have two options now. We need to get into that bootloader so we can crack that password, right? So now we've got a password hash. If you have spare GPUs and you want a challenge, I'm going to throw this password hash in the description of this video, and I welcome people. If you've got GPUs laying around, maybe you were running a a Bitcoin mining operation, right? And you've got a bunch of GPUs laying around and you're sad because crypto has crashed, right? And you're thinking about selling off those GPUs. Maybe you should keep them for just a little bit more and try to crack this hash. Or the other option that we have, if we can't crack this hash, is to replace this hash in the firmware, and then for me to write the firmware back, a new version of the firmware to this chip. So in our next video, that's what we're going to do. We're going to modify this firmware file with a known hash of a password that we know ahead of time, and then we're going to try to get into that bootloader and switch over to booting into the old version of the root file system that we can get the debug shell with a button press. So I'd like to thank you for watching this video. This has been an exciting journey into reverse engineering this device. Reverse engineering is never straightforward. It's always a journey of roadblocks and then getting around those in creative ways. So I hope this video has been insightful to see some of the just all that raw process. So thank you for watching. Please continue to like, comment, and subscribe. Tell me what devices you'd like me to look at in the future, and what you like about the videos, what you don't like. Thank you, and have an awesome day.